So today we're going to talk about vectors in the real set in the vector space of Rn. So what is Rn? Like we talked about in the lectures, we identify Rn with a set of column vectors in length n. We also noted that this choice of representing Rn as a set of column vectors is arbitrary. But it's just a standard in math that we all agree to follow. So we identify Rn as a set of column vectors on length n. So when we say any vector x belongs to Rn, it is the same as saying x is a stacked vector of length n, where each element of x belongs to the set of real numbers. So xi belongs to R, and x is a stacked column vector of all these elements that belong to the real set. When we're talking about, so that's how we relate it to vectors that we've studied before. Now when we're talking about matrices, which are two-dimensional, we can extend this definition in the sense that now matrices are a collection of rows and columns, and we define columns to be, vectors. We take column vectors and we have a bunch of them in our matrices. So we can write our matrix as a set of column vectors. A set basically means like a collection of column vectors. So if you had a matrix, a general matrix of n by m dimensions, you can write it as A1 column, A2, first column of A, second column of A, and the mth column of A. So each column of A is now in Rn. So the jth column, or any j in 1 to m, belongs to Rn, and that's how we can write our matrix A in a more general formulation within this setup. Now, given a matrix A with the same logic, here it's a 3 cross 3 matrix, so your n is 3 and your m is 3. So we can say that this matrix is a set of 3 vectors in R3. So it's a set of 3 vectors of length 3. What these 3 vectors for this matrix are going to be, well, we know from our column partitioning that it's going to be, these 3 vectors are A1 column, second column of A, and the third column of A, which is I wish I left more space. Okay, which is 1, 2, 5, second column of A, which is 2, 5, 6, and the third column of A, which is 3, 6, 8. And A is a set of these columns, and each of these columns, they belong in R3. They're made up of 3 real numbers. So that's a general definition of a vector in Rn and how to understand it. The way that we've used these in class is that we've defined vector addition, and we've defined scalar multiplying a vector. So as a review, I think we're good on it, but I'm still gonna write that down. We defined in class vector addition in that if x is a vector in Rn and y is a vector in Rn, so let's say x is x1, x2 to Rxn and y is y1, y2 to yn, then x plus y is given as x1 plus y1, x2 plus y2, so on, xn plus yn. Similarly, we did scalar multiplication with vectors. So any scalar 2, say, multiplied with a vector x1, x2, x3, you get 2 times, let me put that like, let's say alpha 1. Let's make it general. Alpha 1 times any vector x in Rn is given as alpha 1 x1, alpha 2 x2, and so on to alpha 1 xn. Now we're going to use these things into defining linear combinations of vectors wherein any vector, let me check if there's like people here. Okay, so we're at linear combinations. So any vector v in the space Rn, which means v is a stacked column vector with n entries in it, it is said to be a linear combination of vectors v1, v2 to say m vectors vm that belong to the same, that have the same length, so have n entries in them, if there exist real numbers alpha 1, alpha 2 to alpha m such that this condition holds true. So we're going to be using our 2 definitions of the vector algebra, which is the vector addition and the scalar multiplication. So when we write alpha 1 v1, we know how to write it down in a vectorized form, and we also know how to add them together. So we're set in terms of our definitions, and we know how to write any vector as alpha 1 v1 and how to compute it in any general space Rn. And if we're able to find such a combination to be true for our given vector, then we say that that vector is a linear combination of the given vectors. Now, using this formulation, let's try and solve some examples. So let's say our v vector, which is this one, was 8, 1, minus 8, and the given vectors were v1, v2, and v3, if we're able to find alpha 1, alpha 2, alpha 3, here see that v, in fact, like all of them, v, v1, v2, v3 belong in R3 because the length of that vector is 3. So let me define my vectors alpha. Let there be, let's assume there is alpha 1, alpha 2, alpha 3, such that V is a linear combination of V1, V2, V3. So I can write V as alpha 1, V1 plus alpha 2, V2 plus alpha 3, V3. Now if I'm able to find these alpha 1, alpha 2, alpha 3, that means indeed V will be a linear combination of V1, V2, and V3. So let's see if we can do that. So let's write this out, and from this equation, I get 8, 1 minus 8 is equal to alpha 1 times 1, 2 minus 6 plus alpha 2 times 5, 1, 6 plus alpha 3 times 0, 0, 2. Now, if you want to solve this, I can write this down as equation with 3 variables and 3 unknowns. So let's do that here on the side. I can write this down as alpha 1 plus 5 alpha 2, or actually, let's open this up. This means 8, 1 minus 8 is the same as alpha 1 plus 5 alpha 2 plus 0 alpha 3, 2 alpha 1 plus alpha 2 plus 0 times alpha 3 minus 6 alpha 1 plus 6 alpha 2 plus 2 times alpha 3. Now we also know that two vectors are equal if each and every entry of those two vectors are equal, which means first equation can be written as alpha 1 plus 5 alpha 2 equals 8. Now I'm going to solve it the normal way because it's an equation in 3 variables, 3 unknowns, but we know a better way of solving this, which is using LU and then forward and backward substitution. But to keep it short, for somebody who's doing it by hand, I'm just going to use normal substitution. I'm going to write the first 2 equations, which are in alpha 1 and alpha 2. So 2 alpha 1 plus alpha 2 equals 1. And from here, I'm going to get let's just substitute it. So I'm going to do, should I just, let's see if I have more space here. I'm going to fix the spacing in here, but yeah, let me put these down here so that it's easier. So I get Alpha 1 plus 5 alpha 2 is 8. Get 2 alpha 1 plus alpha 2 is 1. And I get minus 6 alpha 1 plus 6 alpha 2 plus 2 alpha 3 is minus 8. If I sit down and solve these, let's do it for just this one, and then I'm just going to use the solutions. Let me call these 1, 2, 3. I'm going to add 1 and 2 and subtract 3. So that becomes 3 alpha 1 minus 6 is 9 alpha 1. I am going to eliminate. Wow. Actually, let's just do it the normal way. Okay, so alpha 1 from the first equation, I'm going to use this. From 1, I get alpha 1 is 8 minus 5 alpha 2. Put that in 2, I get 2 times 8 minus 5 alpha 2 plus alpha 2 equals 1. This is 16 minus 10 alpha 2 plus alpha 2 equals 1. And then this becomes 9 alpha 2 equals 15, and alpha 2 equals 5 by 3, I guess. Let me check. I think I made stupid error somewhere. So no, that's fine. Okay. And then alpha 1 is 8 minus 5 times 5 by 3. This becomes 8 minus 25 by 3 minus 1 by 3. And now replace all of that in equation 3, and you get minus 6 alpha 1 becomes plus 2. 6 alpha, oh wait, this was alpha 2. My bad. So minus 6 times alpha 1. Oh, I have to find. Yeah. So alpha 1 is, this is alpha 1. Damn it. This is alpha 1. So then alpha 3 is 6 times alpha 1, which is minus 2, minus 6 times alpha 2, which is minus 10, minus 8 by 2, which is minus 10. So I got alpha equals minus 1 by 3, 5 by 3, and minus 10. Let's see if that's true. I write alpha 1 is minus 1 by 3. So this becomes minus 1 by 3 minus 2 by 3. This becomes minus 2. Oh, plus 2. Plus alpha 2 we found was 5 by 3. So it becomes 25 by 3, 5 by 3, 10. Plus alpha 3 is minus 10. So this is 0, 0, minus 20. Now is that true? Let's see. So 24 by 3 is 8. And it is indeed true. So we could write down v as a vector of with alpha 1 equals minus 1 by 3, alpha 2 equals 5 by 3, and alpha 3 equals minus 10. So V is indeed a linear combination of V1, V2, V3. For this one, we're going to do the same thing. It's just a two-dimensional column vector. We write down, so V is a linear combination of V1, V2, V3. Now, the second part, we do the same thing. I'm going to give you the answers. So alpha 1, you should find out to be 2. Alpha 2, you should get 1. And then alpha 3 should be 3. If you want to check it, we can quickly check it. I write down alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3. And I get 2 times this plus 1 times this plus 3 times this, which is 6 plus 2 plus 3 and 8 plus 2 minus 3. And this you will find is equal to 11. And 7 equals V. So you know V is a linear combination of V1, V2, V3. One more time. Let's see if we can do this for this example. I write down V is alpha 1 v1 plus alpha 2 v2. I need to find alpha 1 and alpha 2. From this, I know that V, which is 754, equals alpha 1, 2 alpha 1, 3 alpha 1, that is alpha times V1, 2 times alpha 2, and 0. So your equations are alpha 1 plus 2 alpha 2 equals 7, and 2 alpha 1 plus alpha 2 equals 5, and 3 alpha 1 equals 4. Let's choose these two, because we can only do two equations and two unknowns. From this one, I know alpha 1 equals 4 by 3. I put it in my, let me name these actually. So let's call this A, B, C. From C, I know alpha 1 equals 4 by 3. Replacing in B, I get 2 times alpha 1, which is 4 by 3, plus alpha 2 equals 5. So alpha 2 equals 5 minus 8 by 3, which is 15 minus 8 is 7 by 3. Now, this should satisfy equation A. Now let's see if it does indeed satisfy equation A. I write down equation A as 4 by 3 plus 2 times 7 by 3 equals 7, which implies 4 and 14 is 18 by 3 equals 7, which is not true. So, which means we could not find a set of solution alpha 1 and alpha 2 that would satisfy the condition A, B, and C. Thus, V is not a linear combination of V1, V2, V3. Which we know sometimes can happen when you're doing equations with two unknowns and more equations and fewer number of unknowns. Can be what we call an over-determined system, but you don't have to know that. Yeah, so that is how you would generally approach problems that ask you if some vectors are linear combinations of other vectors. And we use this, and we'll see these in lectures, as we use these to solve the general AX equals B, which we've been doing for quite a while. And it gives us some interesting results, which we'll explore through the course of the lectures. Let me take like a slight look at okay. So now that we've seen linear combinations, the next thing that we've talked about in the lectures is linear independence. So a set of vectors v1, v2, v3, vm are called linearly independent. And one notation to note here, you write a set in curly brackets. So a set of vectors, the way to read that is a set of vectors, v1, v2, vm, are linearly independent if and only if the real numbers alpha 1, alpha 2 yielding the linear combinations of vectors adds up to 0 are trivial. So the only way that we can satisfy this equation is if alpha 1, alpha 2, alpha m are 0. So another way of writing that down is that if we satisfy this equation, it is the same as saying will always hold, like alpha 1, alpha 2, alpha m equals 0 will always hold and will be the only trivial solution. As we talk further in class, we'll see why this is important, but for now, let's just get comfortable finding out how to solve for linear independence, how to say if two vectors are linearly independent. So, using this definition, we're going to try and find out if the given set of vectors are indeed linearly independent. So for the first problem, let's dig in. Our condition is this. So let's write down. Let's assume that that's true. So I assume some alpha 1 times v1 plus alpha 2 times v2 equals the vector 0. Open this up using vector algebra. You get 4 alpha 1 plus 2 alpha 2 and alpha 1 plus 3 alpha 2, and this side is zeros. Solve for these, you get 4 alpha 1 plus 2 alpha 2 equals 0. From here, I can get alpha 2 equals minus 2 times alpha 1. And then from the second equation, I get alpha 1 plus 3 alpha 2 equals 0, which implies replacing this in here, I get alpha 1 plus alpha 2, 3 times alpha 2, which is now minus 2 times alpha 1 equals 0. And then you get alpha 1 minus 6 alpha 1 equals 0. And then I get alpha 1 equals 0. And I also get make it clearer. Alpha 1 equals 0, right? And then we replace this back in here. It's making it super obvious. I get alpha 2 equals 0 as well. So we found that alpha 1 and alpha 2 are zeros. Thus, v1 and v2 are linearly independent. Let's try and do this for this problem that we already found a solution for. So right here, it's the same set of vectors. I renamed V to be V4. We already found that V is a linear combination of these vectors, so we know empirically that they're not going to be linearly independent because one of them can be written down as a linear combination of the other. And we will see how these two concepts are equivalent when we try to find alpha 1 and alpha 2 for this case. Remember, we know for a fact that V4 is equal to, what was my, from this solution, I know alpha 1 is 2, like the alpha vector is 2, 1, 3. So my V4 is 2 times V1 plus 1 times V2 plus 3 times V3 from previous problem. So it should not be linearly, we shouldn't find it to be linearly independent. But let's see how we would do it mathematically. So I write alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 plus alpha 4 V4 equals 0. From here, I get 3 alpha 1 plus 2 alpha 2 plus alpha 3 plus 11 alpha 4 equals 0. And 4 alpha 1 plus 2 alpha 2 plus minus alpha 3 plus 7 alpha 4 equals 0. So now I have 4 equations and 2 unknowns. Is there a way to solve it? Actually, no. But I know for a fact that I found these before. And I'm just going to put those in and see what happens. So I know, let's put alpha 1 equals 2, alpha 2 equals 1, alpha 3 equals 3, and alpha 1 equals minus 1, and see if we can actually solve it. So from here I get 3 times 2, plus 2 times 1, plus 3 plus 11 times minus 1. What does this become? 6 plus 2 plus 3 minus 11 is 0. So this checks out. Four times 2 plus 2 times 1 minus 3 plus 7 times minus 1 equals 0. This becomes 8 plus 2 is 10. 10 minus 10 is 0, so this checks out as well. So I somehow, with magic, found the set of alphas that satisfies this equation. So I know for a fact that V1, V2, V3, V4 are not linearly independent. All right, and with that, we move on. I will post the solutions that we found to the drill problems online. And we're now going to move on to the Julia portion of the recitation. So let's get the Julia code on. There you go. So we're going to talk about functions in Julia. As we've been working with project 1, which hopefully is going better, we've seen that a lot of the code has been written down into functions that we've been calling time and again. So I think it makes sense that we understand how to write our own functions in Julia and how to maneuver around them. So why do we actually need functions? We need functions. I thought I was going to be doing plotting, but not today. So we need functions so that we can specialize a block of code that does certain operations for us, and then we can keep calling those operations as we progress through our code. And so that way, I don't have to write everything sequentially. I can just save a set of the code separately and call it in my code later. So the way to do that in Julia is to, we write down the keyword function. Then we specify the name of the function, which we're going to use to, so that's what I'm going to call my function. My function is called calculate sum. And then I pass it a list of arguments. So arguments are like inputs to a function that can be used inside it to manipulate, to get results, or just to pass values or variables from the calling code to the function. So here my function simply takes some values x and y and returns the sum x plus y. The return statement is used to return a value from the function. So everything I do inside this function, I can't access the sum variable outside of it. So if I have to get the value out, I have to return the variable sum. As soon as any function hits the return statement, the control flow goes to the statement right after the function call statement. This will make more sense in a while, but so you run that in Julia, and it gives out an output like calculate sum generic function with one method. So I've written a function with one method, which basically just means that there's only one definition of this function, which is what I've defined it to be. It's a unique function, a user-defined function. Now, x and y are the arguments to this function, and then the computation is saved in the variable sum. And the output is returned using the return statement. This is how you'll see all functions be in Julia. Now, how to call this function, how to get that sum, is just simply say calculate sum, the name of my function, and then pass it as arguments 2 and 3. So what this will do is my compiler will say, okay, calculate sum. I will go to wherever I've saved the function calculate sum. I'm going to assign the value 2 to the variable x and the value 3 to the variable y. And I'm going to instantiate a variable sum where I give it 2 plus 3, which is 5. And then I'm going to return that value 5. So when I run this block, my answer should be 5, which is what you'd expect it to be. You can also save it in another variable. So I call it save sum. And you can pass it floating point, and it will do the same thing. Now x will have 2.3 and y will have 5.677, just some random numbers. And when I run it, save sum will have the value 7 point, whatever is the floating approximation that went on there. So that is basically how you write functions in Julia. If you understood this, you're probably going to be good for the most part. But if you want to get into the nitty-gritties of how we're doing things in Julia, we're going to move on to methods. So when we're defining functions here, we note that x and y could be anything. I gave them 2, I gave it an integer, I gave it a floating point number, and my calculate sum could figure out what to do with them, and Julia typecasted it. But what if I was to give it something like calculate sum, a number and then a string, and then I asked it to add them? Now, as far as I know, that is not defined in Julia. So it'll say method error, and it'll say no method matching the input that I've given it, which makes sense. So to avoid errors like these, you can do like like your first intuition will be, okay, so we shouldn't try and add those two things. What we should do is we should say that if x is a number, and then we should make sure that x and y are both numbers before we actually go about doing computations in our x and y. So to write something like that, you'd say function if defined calculated sum. That's just what I chose to call it, x and y. I said if the function type is number, so this operator basically means of the type number or any of the subtypes of numbers. So like number, integer, floating point, all of those in the tree, in the hierarchy that Julia operates in. If you're any of those types, you're okay. And so that should be true for both x and y. So anything that is not a string, you're good. Or a vector. And otherwise, just say your types are inconsistent or there's an error in your types, and return. You see how there's nothing there? So the reason I put a return there is that that's how my function will know, okay, there's no point staying in this function anymore, and I should return after I've printed out this error in types. There's nothing else to do in that function. So I define that function, and it should be able to handle an input like this, and it should give me, okay, there's an error in your types. Like, you shouldn't be doing that. And it still works when I give it 2, 3, which is where it goes in this part of the code and decides, oh, 2, 3, 2 is a number, and 3 is also a number. So I can return x and y. let's say I gave it like a vector. So 1, 2, and 3, and okay, let's make it like compatible. Now, in theory, vector addition is defined, but when I run this, it's going to say error in types. Why is that? Because x equals this vector 1, 2. It goes in here. Is vector a subtype of number? No, it isn't. So it goes into this else, and it says, oh, I don't understand how to do this, and it says error in types, like better define your functions. So that's one way to go about it. But then I have to take care of each and every type, and there's just one function, and it's just hard to deal with. Each and every one of my functions will have to be like, okay, if statement, if this is the type, and this is the type, then this is the operation. If this is the type, and this is the type, and this is the operation, which is cumbersome. So the way that Julia handles it is using multiple dispatch. Now, what does multiple dispatch mean? It means that I can write functions that have the same name, but I describe the type of the input argument that they're expecting. So if I had to define a generic sum that can handle a string as well as a number, and it identifies when I give it 2 strings, it says, okay, these are 2 strings, I should call this definition, and I should concatenate the strings, and when I give it numbers, it looks at, okay, I was passed numbers, I should go to this definition of the function, and I return x and y. So let's run this cell. In here, I've specified a function, generic sum, which gets the arguments x and y of type strings. Then I define another function with the same name, x and y, which are both numbers, and then you see that the generic sum is a generic function with 2 methods. One was the one defined here, the second one was the one defined here. Now let's say I have like 10 of these, and I want to see each and every one of these methods. I just write the function, I use the function methods, and I pass my function in there, and I get something like this. So it found 2 definitions of my function. One is the generic sum that has 2 string arguments, and the other is the generic sum that has the number arguments. In the 17th cell, so this cell, and in the 18th cell, this cell. And this is where you read the line numbers. This is something that will come in handy when you're debugging your code, usually. So when I run this one, it should identify that I'm passing it 2 strings, and it should go to the definition of the function that is defined in cell 17. So let's try running this, and I get hello world. So that's perfect, and it didn't give me an error. If I gave it 2, 3, it found the right definition. If I give it 1, 3, now the point to note here is that this is an integer and this is a string. None of our function definition handle a string and a number. So this should, for all intents and purposes, and I've coded it this way, I needed it to give me an error. So it does say a method error. It says no method matching a function generic sum of type int64, which is the element 1, and of the type string, which is this name that I passed here. It says the closest candidates are, this is how you can see how Julia's working. What it does, it looks at the function call, and it says, okay, if I'm going to look at the first definition, which was the string in string, I try and match the int64 type with the string type. It doesn't match, and it returns an error. Okay, fine. Let's check the second definition. It goes to the second definition, which is in the 18th cell, which takes two numbers. And then it says, okay, int64, okay, it's a subtype of number. I'll look at it. But then it looks at the second argument, and it says, well, that doesn't match. That's not a number. And then it gives you a method error. So how can we use this to our advantage? We use it to our advantage that I can have a single function, like I can define a function with a single name, and it can do multiple things depending on the input, and I don't have to change a thing. I can give it strings, and it'll concatenate them, and if I give it numbers, it'll automatically add them. Another thing that is interesting in Julia is that you can return multiple values from your number. The way that this is done is that Julia will return a tuple. So a function, let's say I define a function called sumDiff, which takes two numbers x and y, and it returns x plus y, comma, and also x minus y. So I just return it, and this will automatically be a tuple. How do I know that? Well, run this cell, and you see that the type of the output from this function is a tuple of int64 and 64, which is because of the input I gave it. So a tuple, as we covered in lectures, in math in itself is just an ordered list. And tuples in Julia are used to have ordered list of variables which you do not want to change values of later. All of that you can ignore. What that matters is that if you wanted to assign the value, so like sum difference 2, 3 gives you 5, minus 1. So x plus y 5, x minus y minus 1. I can assign tuple values to variables simply like this. So I just write a tuple a comma b is equal to this tuple sumdiff 2, 3, and it assigns them to the variables automatically. So my a is 5 and b is minus 1. So if you look through your project, when you go to the task 3 and you're doing the data parser function, you'll find that there's a big list of like point data and then intensity data, and it's all in a tuple. The only reason we could do that is because Julia lets us assign all of that easily, and we could return multiple things as big as like 7 million points in our point cloud, the different arrays, put them in an ordered list, pass them, give them out as the output of the function, and then in your main code, you can literally just call it and assign it in a similar list, and it's easy to do. We can also index members of a tuple exactly how you would index arrays using the square bracket. So if I wanted to access just the first element of this tuple, which is basically just the sum, so x plus y, I would say C is sumdiff 2, 3, and 1. And you remember how I assigned A to be the first element of this sumdiff? Using the tuple, well, it's comparable to when I do this separately. And I see that it's true, like C and A are true. So we're good. Another thing, I think we looked at it in the previous recitation, and we used it to define arrays from functions, is a compressed format of defining functions. So one-line functions, you can just define like function of x comma y is x plus y. And then I can do something as simple as this. Now that we understand how to define functions and the way to use it, one thing before we move on ahead is we want to understand the scope of our variables. Scope is like a fancy CS term. It basically just means a part of a code where your variable is valid, and when it is valid, you say that my variable is in scope. So let's say I define a variable x equals 20, and I look at the value of x. Well, it's obvious it's 20. Now, let's say I define a function f of x, and you will notice that this value, this x, has nothing to do with the x that we've defined here. So now at this point in our code, x will be equal to 20. And inside this function, x will be whatever has been passed in this x. So I call it display x should give us the value that we give it here. So it should be 10. And then outside the function, it doesn't care what happened here. It got assigned the value 10. It doesn't care. Your x is still the same. Your x is still 20. I could also change the function in here. I could say x is equal to 50 and run the same thing. And it'll say that, OK, it doesn't matter what you passed here. X got reassigned the value 50. But again, that only matters inside this block of the code. It doesn't matter when you're outside of this function. Once you hit the end block, it doesn't care what was inside, what happened inside the function. And when you say display x, it still prints out 20. You should also notice that this is true for like different blocks of code. So if I was to write like for I equals 1, 2, 3, or show I, and then outside of it, when I say show I, it'll say variable I not defined. Why? Because anything that happened inside a block of code, which goes from this for to when I receive this end, now my variable I is just not in scope. Like it can't be accessed. It was just defined inside that block of code. So it gave me I not defined, but inside the function, I was still valid, and it went on to 1, 2, 3, and then it crashed. It didn't care. Like I ceases to exist after this block of code identified using the end statement. So after your end, everything that was in a particular block of code, you lose the memory of it. Okay, so now that we understand scoping, we understand for loops, we understand if statements, we understand how to write our own functions, we have a functional understanding of how to code. And it will be interesting, and you're encouraged to look at codes, look at coding problems online and trying to solve them on your own. Examples of these coding problems, there are a lot of them out there. The one that I am going to go over with you is a palindrome problem. So your problem is to write a function. Let me see. Yeah, so your problem is to write a function that returns if the given number to it, if the argument given to it, which is a number or an integer to be specific, is a palindrome or not. So if the number is 1 to 1, then your function palindrome of 1 to 1 should return true, because 1 to 1, once you reverse it, it is again 1 to 1, so the number is a palindrome. So you're right. So the way that I'm going to solve it here, and there's multiple ways to solve it, go at it, is I'm first going to write a function that reverses the number given to it, and then I'm going to check in my palindrome function if the original number and the reverse number are the same. So how would you do that? So I want to reverse a number. I recognize that any number can be written as like in powers of 10, because we use the decimal base, right? So to reverse a number, I'm going to start, I'm going to keep dividing my original number by 10, and I'm going to keep saving the remainder. So if you're not getting this, humor me for a second and look at my code. So I define a number rev equals true, and I'm going to use a while loop. So I'm going to run this loop till the time my number doesn't become equal to 10. And what I'm going to do is, this is going to be my final answer. So my reverse number is going to be in here, and this is my original number. I'm going to say that I'm going to extract the remainder when I divide it with a 10. So that should give me, if I'm going at it for the first time, it should give me the last number, the number at the unit place of our question. And I'm going to update that. I'm going to build the reverse of the number will then be whatever was there before times 10. So right now my reverse is 0. I get the remainder of 10. So I get the thing from the units place. I multiply it and add it to the remainder, add the remainder to it. So I'm going to extract the unit place and keep building it by shifting it to the beginning. And then what happens, I need to also update my new number is then the integer value of the division int 4 of x by 10. So the integer value of when I divide my number by 10. So I want to update my number. I extracted the unit place, and then I divided by 10, so that my number is now essentially, whatever was on the tens place is now in the units place. Put the end in here, and that should be it. And then you need to return reverse. So for the first time, let's have it show the remainder for each iteration. And I'm going to pass it the number, let's say 1, 2, 3. So our answer should be 3, 2, 1, right? Let's see. So in the first go, it says, okay, x is 1, 2, 3. When I divide x with 10, I get the remainder, well, x can be written as 120 plus 3, so I get the remainder 3. Then my reverse string, rev for now is 0. So my reverse string becomes equal to the remainder, which is 3. So my rev now has 3, remember that. Or actually, let's just print that out. At the rate, show the reverse string and also show our original number, right? So show x. There you go. So at the first go, your remainder is 3, the reverse string is 3, and now your x, after you've divided it, from 123, it becomes 12. Now, you go back in the loop, you look at is x equal 0? You check, okay, no, x is not equals to 0, x is equal to 12. So I continue on, and I see my remainder is 12. When divided by 10, I get the remainder 2. Now I update my string to be whatever it was 3. 3 times 10 is 30. 30 plus the new remainder is 32. So I get 32. And I update my x by dividing it by 10. And 12 by 10. And when I round it off, I get 12 by 10 is 1.2. I round it off, I get 1. I go back, I check for the condition in my while loop. I see x equals 1. So x is not 0. And I go, okay. Then I find out the remainder. Like, okay, x is 1. 1 divided by 10 gives me the remainder 1. So my reverse string, which is 32, I say, okay, update it like 32 times 10 plus 1, which is 321, which is what we get here. And then I update my x again to be 1 divided by 10 is 0.1, and then I round it off and it's 0. Then I go back, I check again, and I get, oh wait, x is equal to 0, so I should stop. And I step out of my loop right here to my return statement, and I return whatever was in the value rev. Now, you should note why I had to do, I had to do rev equals 0, otherwise rev would be garbage. But if I didn't define rev outside of this loop, I would have lost all memory of what happened inside the loop. So you have to initialize stuff outside of your loop as well. So now it makes sense. I said reverse num 1, 2, 3, and I got the value 3, 2, 1. So this function works. Now I'm going to remove all these show statements. Just to keep it concise, we know that the function works. I run it one more time to define it. Amazing. Now, all that's left to do to check if it's a palindrome is to check if x is equal to whatever is the reverse of x. Well, then return true. And in all other cases, return false. And then end, and that's it. So palindrome of 1210 is obviously false. Palindrome of 121 is true. So you'll find a lot of practice questions online. Feel free to post them on Piazza if you're stuck on any of them. If you find some interesting problem, discuss it with your peers. And I think the only way to learn Julia is just by, basically just doing more of it. So practice makes perfect. And if you want me to cover more examples like these, let me know. But I'll try and bring in as much coding problems as I can. So last thing was, we found a question online which I found was very interesting. Can you show me in Julia that computing inverse of A is equivalent to solving AX equals EI for I from I that goes from 1 to n? So we can indeed do that. And yeah. So the way that I'm going to do it is I'm going to just define a matrix A. So basically, we want to show that solving for x from this equation should give us different columns of the inverse of A. So let's define a matrix A using linear algebra. Let me run that block first. determinant is 1. I defined a matrix A, and I also found the inverse of A, which takes a little bit of a time, but this is the inverse of A. And now we want to prove that we can build this, like each column of this can be found from AX equals EI, where E is the column vector, the special column vectors that we saw. So for a 3 cross 3 matrix, the column vectors there'll be 3 column vectors with 1 here in the I1, 1 here in the E2, and 1 at the last position in the E3, which is what we did in class. So I'm just going to define the E1, E2, E3 vectors. Then I'm going to solve it using LU instead of doing the inverse, and then we're going to see that those are actually comparable. So I solve L and U, and I just want to check that my LU is actually equal to my A matrix, and I made sure that the P was just not, I wasn't permutating any variables because I just didn't want to deal with the P right now. So it's 2, 4, 5, 1, 3, 3, 2, 5, 6. So LU is equal to A. Now what we're going to do is we're going to solve this using LU. AX equals EI. So I define the functions for doing backward and forward substitution using the most simple formulation that I could find in homework 2, so you all should be able to follow. The only thing I do is I just put them in functions. I define A, and I fix the sizes of, fix the dimensions of A. So A should be an array of float 64 with dimensions 2, and B should be a vector because L and U will be 2-dimensional, and then B will be like EI or YI. So now that I have that, I want to solve for AX equals EI for all I from 1 to 3. And the easiest, simplest way to do that is I'm going to define y1, which is u times x1, which is how we do, which is how we solve in forward and backward substitution. And I say forward. So my y1 is u times x1. And so I solve it using a forward, and then my equation becomes L times y1 equals E1. L is lower triangular, so we do forward substitution. I write this down and I say L comma E1, and that should be my y1. And then for the second equation, I know that my u times x1 equals y1. So I do, and u is upward triangular, so I do backward substitution, and I find out x1 equals backward substitution of u comma y1. So now that I have x1, let's just double check it. I should have found x1. If ax1 equals E1, I should have found L times U, which is A, times x1 should be equal to E1. And let's see if that's true, and that is. Similarly, I will find x2 and y2 and x3 and y3. Just copy the code, and that will give me my different columns of the inverse that I just found. And